And let's give it a name, exercise session 8. So we are going to work with the empirical exercise from the 7th chapter of this book. So the empirical exercise is 7.1, this one. So it is based on the same data set. Basically, it concerns the same problem, how smoking affects the birth weight of a newborn. So now it's empirical exercise number 7.1. So we have found in the last exercise session, we have found that there is a negative causal effect of smoking on the birth weight. So if mother smokes, then the average weight of baby decreases by 217 grams. So now we need to apply everything we know about the hypothesis tests, and also, as I promised, I will show you some tricks how to extract the necessary statistics from the regression results. So we keep this part with the data frame load. So this is wait, sorry, I need to run this part first, and then this. Yeah, so this is not needed, so we can cut all these graphs. They are not needed for our purposes. And in the empirical exercise, first, so to begin, they ask us to run 3 regressions. So to begin, run 3 regressions: birth weight on smoker, birth weight on smoker, alcohol, and number of prenatal visits, and also the force control variable, or like the force regressor, and additional control variable is whether lady is unmarried or not. So let's do this in the same way. So we have it already, we have all these regressions, but in order to kind of make some nice things later, let's change somehow this code. I have already changed this. Probably from the previous version you have like formula, blah, 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 and then also you had results. So let enumerate them somehow. So for example, let's give this a name formula 1, model 1. So also here we need to change it to formula 1. So results 1, and here results 1. In order to store all these objects separately with the first regression results. So add 1 to the end of all these objects. So run this, nothing changes, the table is here, but now your regression results of this specification, they are stored under name results 1. Okay, so we can drop this. So, and the second regression, we do the same. With the second regression, formula 2, model 2. So here we also need to refer to formula 2, because now we are referring to this object. Results 2, model 2, and results 2. Everything is okay. We can run this part and we can get this table. So let's cut this part. So this is not what you have from the previous exercise session, so don't worry. We will discuss it shortly. Let me hide this from you for a second. So we will discuss what is this and how we can use this. Let's do the third regression. So we need to regress birth weight on smoker, alcohol, number of prenatal visits, and marriage. So we can copy this part of code from the previous cell, insert it here. So first of all, in the formula, we change the formula and add one additional variable, merit. The name of this formula is formula 3, model 3, formula 3, results 3, model 3, and results 3. So we change everything here. And once we, what's wrong? Unmarried, sorry. The name of the variable is unmarried, not married. Unmarried, and here we also need to provide unmarried. Yeah, so finally we have these regression results. Are you following? Is everything okay?
Yeah, very clear.
What about other students? Zhao Xuan, have you solved your problems?
Yes, I already said yes.
Perfect. Sin no. What about you?
No problem.
I couldn't hear you well, but I hope everything is okay. So nice. We have 3 models. Now, if you have already read the book, there is a suggestion. The suggestion is the following. So once we have all these model specifications regressed separately, it is not very useful to compare these tables like, okay, so let's look at this table, then we need to scroll to this table, then we need to scroll to this table. It's quite not very nice. So what we can do, we can put all these regression results side by side in this nice table. And this is basically, this kind of table is the usual way how people represent the regression results for different model specifications in some publications, in their articles, in some practical work. If you need to display different models, you will always construct such tables. And in this table, you will have in the first column, you will have the list of variables that you use, probably some statistics that you want to display to the reader. And what is the most important here, you will report the coefficients and you will report the standard errors for these coefficients in order to let readers make some hypothesis testing, construct confidence intervals, and all these necessary things that we have been discussing. So our goal is to build this kind of table, and that's what I already made here. So we need to use the following line of code. So I will probably drop it to chat, and you can just copy this from chat, because it's quite complicated what we need to load and how exactly it should work. So check chat and copy this piece of code and insert it here. So we can call this create a table with regression results from 3 models. Right, so this is the first thing that we need to do. So the second thing that we need to do is the following. So let's call this kind of nice table, like the object that we are creating, nice table. And this is the function that we are going to use, this summary underscore call. So this nice table equals summary underscore call. And then look, and then the only thing that we need to do is to provide these objects. So we have these three objects called results. Results 1, results 2, results 3. These objects are kind of like boxes. Inside them, you have a lot of information. So all this information that you have in this table is stored inside the object which is called results 3. And then you somehow unpack this object with different methods, with different with different functions, and receive whatever you want. So we provide the following: so summary call, and then inside the brackets, in square brackets, we write the names of these models: results 1, comma, results 2, comma, results 3, comma. No comma, nothing else. So this is the first step that we can do. If we run this part, sorry, we need to run this part first, and then this part. If you run this part, so nothing happens. Why? Because we just store this nice table as an object. Now we need to call this nice table. So let's write it like print nice table. And you have something like this, or at least you are expected to have something like this. Do you have it?
Yes.
Great. So you can be very proud of yourself because now you made something really useful and really important in econometrics. So all people who publish their papers, they create the tables like this. Well, we can make it look better somehow. Why? Because first of all, you see that the order of these variables is not very nice. You see that the first goes intercept, then for some reason we have r squared adjusted r squared, and then we have variables: alcohol, number of parental visits, smoker, and unmarried. So the order is not very nice. So this is the first improvement of this output that we can do. So let's go back to this function summary call. Let's put comma, and then we have this attribute here, regressor order. So we can write it like this. So regressor underscore order equals, and then in square brackets, in quotation marks, you need to list the order of regressors that you want to display. Usually, the first row, in the first row, we display the regressor of interest. In our case, this is smoker, right? Because we want to show in the first line the effect of smoking on the weight of a newborn. So we write here smoker. Then after smoker, we can basically use any order, but let's use the order that we followed in our regression. So the second is alcohol, the third is NP revist, and the fourth is unmarried. Well, basically, you don't need to specify intercept. The intercept is going to be the last one after you specify this order. Now, if you rerun this cell, you will get this, which looks much better, right? So you, on the first place, you have exactly what you want to display, smoker, and in all the other places you have the variables, the control variables that we included in different regressions. Well, basically this is enough. This is enough for us. But I also want to show you, because look, now this table looks more or less similar to this table. Well, of course, this table looks a bit nicer. We have additional lines here, like control variables, summary statistics, regressor, whatever. But overall, we have the same thing. We also can do this. We also can give these columns names like this, 1, 2, 3, 4, or if you want to give some other names, it's also possible. So back to this function, back to the function summary call, we can put comma, and then we can use these model names. Model names. We can put enter model names. And the same model names equals in square brackets, in quotation marks, we provide names for every column. So for example, 1, 2, and 3. And if you rerun this once again, we have even more table, which is even closer to the result in the book. And the last thing that I want to demonstrate, this is not demonstrated here in this book. So let me check, basically, do they use it later in some other? No, they don't have it anywhere in the book. Well, probably they don't follow this approach. But look, let me show you. For example, in some other books or in some papers, you can find something like this. Let me show you from some paper. Like I can open some random paper which uses econometrics, and when we go to the results part, I guess I was showing this to you. We can find something like this. Yeah, like this. We can find the stars. So the stars are very useful things in order to report the significance of coefficients. Well, there are different approaches. Some authors, like for example these authors, they do not put stars on their regression results. If you look at the table with regression results like this, you see only coefficient estimate, you see the standard error, and that's it. Exactly as we have here. Some authors put these stars near the coefficients. What the stars mean? So let's also put stars to make it better, so we can put here additional attribute, stars equals true. Yeah, and you see that we have these stars. So stars are very useful whenever you don't have these p-values reported. Because we discussed, if you want to test a single hypothesis, we either do this looking at t statistics and comparing them with the critical value, which is in usual case 196 with 5% level of significance, or we can look at the p-value. Stars do the same, serve the same purpose. When there are 3 stars, look what this note here tells us. 3 stars means that p-value is less than 0.01. So, which means that if there are 3 stars, this coefficient is significant at 1% level. If there are 2 stars, this coefficient is significant at 5% level. If there is 1 star, the coefficient is significant at 10% level. Right? So, with this tool, you simply send a message to readers that, for example, smoker is, so this coefficient is statistically significant at 1% level. Alcohol is not significant either here or here. So alcohol is not significant, and therefore, well, the causal effect might be 0. But again, so this is a control variable, and we are not really concerned with the control variables and with their significance. So maybe this control variable is still correlated with the regressor of interest, and we see that it is correlated, and the coefficient from the first model changes from 253 to 217, which means that alcohol was omitted variable, and even though it is not significant here, but still we must keep this in this specification. And also the coefficient on unmerit is statistically significant and has a large negative effect, and which kind of pulls down the coefficient on smoker even more, which means that we somehow improved the omitted variable bias problem from the first and second specifications. So everything else that is given here is not that important, and I can drop it. So we have this nice table. Are you following? Are you okay with this? Do you have the same?
Yes, the table is very nice.
At least with such type of table, you don't need to scroll between different tables like this. Of course, if you need some specific measure from this table, like F statistic, here or here, you can basically look at these tables. But if you just need to compare the regression results, you can do this very simply here. Well, basically, this is also possible to report in this table anything you need from the previous tables. But before doing this, let's try to discuss how to extract necessary numbers from these tables. So if you have this table, so now let's move on and let's discuss some questions from the book. Where is that? Oh, it's 8.1. Okay, so what is the value of the estimated effect of smoking on birth weight? This is in each of the regressions. So we see that the effect kind of becomes smaller in absolute value, which means that these included regressors possibly helped us to overcome the problem of omitted variable bias. We are not sure about all the possible reasons and all the possible variables that affect birth weight of a baby. And we see that R squared is very low, so it means that this set of regressors is not able to fully explain the weight of a baby. But we don't care about R squared because we don't want to predict birth weight. We want to understand what is the causal effect of smoking on the birth weight. So that's why we are not really concerned with the R squared. Well, and we also last time we also discussed that well, probably the quality of food can affect the birth weight. So probably stress and some let's say psychological conditions of mother. And well, it is quite difficult to measure those factors, right? So you cannot get the data how well mother ate before or during her pregnancy, or what was the level of stress of her, or something like this. And we somehow, well, we can somehow use a proxy with her, let's say, average level of income, right? So if her income is higher, so probably the quality of food she ate, and so the level of stress was lowered. That's how we are trying to substitute those omitted variables that we are not able to collect with some variables that are tightly correlated with the omitted variables. Well, basically the question is, do we have something like this? Yeah, we have education and we have age, but we don't have yeah, okay. So we have education, we have age. Education can also somehow report about the, let's say, the background of a lady, and we will try to include this to look what happens to the coefficient. Well, now let's skip this part, construct 95% confidence interval. That's not that important. So all of you know how to do this. You take the standard error, you take the coefficient. Okay, no, well, basically, yeah, let's do this for one specification. So let's construct this, and I will also demonstrate you 95% confidence interval for beta 1 in regression, in the first regression, let's say, in the first regression. Yeah, it would be nice exercise how to work with Python. So we know how to construct a 95% confidence interval. So we discussed with you that all you need to do is to take the coefficient estimate here minus quantile times the standard error. So this is the coefficient estimate, this is the standard error, and the quantile can be approximated with 196, which is not that big deal. But we can make it, of course, we can make it more precise. Well, this is not very nice to take these numbers directly. So we can, of course, we can write something like this, minus 253, 2284, minus 196 multiplied by, this is not a problem, right? So we can calculate this. But how is there any way to extract these numbers as they are? And the answer is yes. Remember that the object result that we create every time when we estimate our models, the object result contains a lot of information. And let's try to extract this information. When we write results 1, and then you put dot, and then you can press tab, like the button tab on the left 2 times, and you will have this list. The list of all possible metrics that you are able to extract from this box called results 1. And basically the one of them is called params, these parameters. And this is exactly the parameters that we want. So the parameters that we estimate with this model. If you run it like this, like you write results 1 dot params, and then you run it like this, you will have both parameters, intercept and coefficient on smoker. Well, what do we want? We want only this number, minus 253. And you know how to deal with this. If we have a list of 2 elements, and we need to extract only one element, and this is the second element, in square brackets we put number 1. That's all. Why 1? Because the counting starts with 0. 0 is intercept, 1 is smoker, the coefficient on smoker. When we run this, well, we have this coefficient. Perfect, right? So we can give it a name b1 equals this. And we extracted this number. No need to type with our hands, whatever we have. So now we need a standard error. Now we need a standard error here of this variable, and we can do the same. So the standard error 1, let's call it like this, SE1, and this is results 1 dot, and then if we also open this list of possible methods that we can use to results 1, and we scroll this, we have this HC0 SE, HC1 SE, HC2, HC3. So you remember that we prefer HC1 standard errors. So we click here, open square brackets, put 1, and this is gonna be the standard error on the beta 1. So this is the way how we can extract from this box, from the object results 1, everything that we need. So also we want to have this t. Okay, so let's do this in the more precise way. You remember how to get the quantile. Wait, before getting the quantile, we want what? What do we need? We need the degrees of freedom. For t distribution, we need degrees of freedom. So let's put it like this, df. Do we know how many degrees of freedom in this model we have? We can also watch it here in the table. It's 2,998, because the number of observations is 3,000 minus 1 and minus 1 regressor added to the model. In total, 2,998. So can we extract it? Yes. The same thing. Results 1 dot, and then we can type df resid, which is the degrees of freedom for the residual. Nothing else is needed, so this is gonna be the number of degrees of freedom. So now alpha is 5%, 0.05, and t equals, I hope you remember this part, stats.t.ppf 1 minus alpha over 2, comma, degrees of freedom. So let's see what we have, like what numbers do we have. Let's check that everything works. So let's print them. P1 is E1, df, and t. Oops. Yeah, we need to load stats here. Imports. What we need to import, I forgot.
From SciPy stats.
Yeah. SciPy. Yeah, so add this part from SciPy import stats. And then it must be working. And we have all these numbers. Beta 1, standard error for beta 1. Let's check that in the table we have exactly this. Degrees of freedom, and as I said, approximately 196, the critical value. So then, if everything works, we can drop this, no need, and we can set up the lower and upper bound of the confidence interval. So usually we can write it like this, LB, which is for lower bound, equals, now we take B1 minus T multiplied by SE1. This is the lower bound, and the upper bound is B1 plus T multiplied by SE1. And now we can print. We can, as you know, we can now provide also some text here. the 95% confidence interval for beta 1 is, and here we can give these numbers, but if you want to somehow make them better, we can round them, of course, with the help of numpy round. Let's store two numbers here and numpy round here. Yeah, and now this is gonna be what? So like this square bracket here, then this is LB, then comma, like this, UB, then this. So what is written here, basically, so we put the text here first, and open the, so in order to have in our text the square bracket, we put the square bracket here in the string, then comma, and we ask for the value of lower bound here. Then we want to have in the printed text this comma again. So after we close the quotation mark, we put this, and we close the bracket, and we have the nice output, kind of human readable with both values. It is not necessary. I mean, if you don't want to do this, you can simply ask for printing LB and UB, and you will have these two numbers, and you're going to be totally fine. At least you will see these two numbers, and everything would be nice. But if you want to make something better, you can always write it like this. There is basically another way how to plug inside the text some variables, but I'm not going to discuss it, at least for now. So this is the way how we can extract from object results 1 or results 2, results 3. Now, if you will change this results 1 to results 2 or to results 3, you will get the confidence interval for all the other models. And we can also compare this with what we have in here. So from 305.8, let's say, to 200.68. Yeah, exactly what we have here. Is everything successful? Should I wait?
It is okay, but this command, this line is very confusing. The print line.
Yeah, again, what you want to have here, you want to have this piece of text, and here in square brackets you want to put numbers. So therefore, everything that is not a number, that is not lower bound or upper bound, must be in quotation marks, and you separate every piece of text from number with commas. So that's why, look, for example, if you keep it like this, you will have only this part, right? But you want after 305.8 to have comma, and this comma is a text. It's not a part of a number. It's not a part of your code. So that's why you kind of, after the comma, this comma is the separator of lower bound LB, which is the object, which is a number, right, that you put here. It is a separator from the text that is going to be afterwards. So basically I can write it like text after here, and you see that what happens here. But I don't want to have text after, I want to have a comma here, right? So then this comma appears, and then after this piece of text, comma, I put comma once again, and I put upper bound. Okay, so what is missing here? I want to put an additional closing square bracket here after upper bound, again I put comma, and this comma is a part of the function print, which separates variable from text, and then I finish my text with the square bracket here. So this is the final result. So every comma which is not inside the quotation mark is a separator of text and variable and the object that you put there. As I said, there are there are nicer ways how you can provide the same thing, but this is the simplest one, so that's why I'm not going deep into other ways. There are some special strings called F strings, where you can also put the numbers and you can format them in place. Any questions here? Is everything okay with the coding? Again, as I said, this part is not important. So the most important is to be able to calculate the lower and upper bound for the confidence interval. So this is just kind of a cherry on a cake, let's say, to make the code readable. So let's think about these two questions, question C and question D. Do we have some evidence that the coefficient on smoker in the first and second regression suffer from omitted variable bias?
And what suffers from which variable?
Here, the coefficient on smoker.
I see.
So do we have enough evidence to claim that in regression 1 and 2, these coefficients suffer from omitted variable bias?
We cannot reject it, I guess. Because
it is not about hypothesis, it is about what. So what is omitted variable bias again? So what happens with the estimate if this omitted variable bias is present?
Oh, it doesn't converge into the probability and
yes, it doesn't converge to the true value, but we don't know true value. And the only possible way how we can check if this omitted variable bias exists or not is to include control variables, to suggest some control variables that are correlated with the regressor of interest and with the outcome variable, in our case, birth weight. And look, when we observe the first regression without any control variables and the second regression with 2 control variables included, what do we see regarding the coefficient on smoker, regarding this coefficient? What happens to the coefficient?
its impact decreases.
Yes. What does this mean regarding the problem of omitted variable bias? Do we have do we believe that
less of bias?
At least we can claim that in the first model this omitted variable bias takes place. It is there, right? Because we see that inclusion of control variables makes changes the value of this coefficient, and this change is large enough. It's kind of like a quarter, right? So, or not quarter, but 20%, like 50 from 253 to 217. It's approximately like 20% decrease, right? So this is the way how you can find an evidence of an omitted variable bias. And what does this mean? It means that you cannot believe to this estimation, even though the coefficient is statistically significant, even though like you have these 3 stars, but you cannot believe that kind of only smoking reduces the birth weight by 253 grams. So this only factor does not have that large effect. Well, okay, so we move to this. And now we are trying to analyze this model. We can compare this model with the next one when we include one also potentially important determinant of a baby weight, which is whether lady is married or unmarried. Because probably if she is unmarried, she needs to work more, she has more stress, and probably this somehow affects both her health conditions and the birth weight. When we include this control variable, what happens to the variable of interest?
It decreases.
Coefficient, the effect decreases even more. So do we believe that this was unbiased estimate?
No.
No, because you see that it still changes. It keeps changing when we include the variables. Well, basically, the idea is, and you have this discussion also in the book, in those chapters that I asked you to read. If you include more and more regressors, of course, you must think about the nature of these regressors, and you need to have some, let's say, expertise in the field about this. You either keep changing this effect and keep kind of cleaning this omitted variable bias problem more and more, or if nothing changes with the coefficient, then at least to some extent you can claim, well, probably we came to the estimate which is close enough to being unbiased. The most difficult part here is that you never know. This is the most difficult part, and this is the most complicated to understand part, that you never know whether here is still, whether the bias is here or not. We don't know. We cannot answer this question. We just need to take this as the part of our reality. Well, maybe we can believe that this is unbiased estimate, but so unfortunately, it's hard to say.
And then if we add years of education, it will.
Yes, we can try. We can try. Well, basically, we can do this, and let's try. Let's try doing this. Let's take this model, and let us. What we can do? We can add 2 more cells here under the previous model before this table. We can put now something like add education, and what else do we have? Age, but probably age is correlated to the education, right? And including both of these variables is not very nice, because, well, years of education and well, we can check.
We may include and look if they are correlated, like if it was in the chapter, and if they are correlated, then one of them will be neglected.
That's true. On the other hand, we can check it in the following way. So let's see data education and age, and we can calculate the correlation. Well, yeah, they are not that strongly correlated, and we can put both of them. And if you look at the correlation of all variables, what do we see? Education is not correlated with either of them, so the largest correlation with age. And if age is not correlated with, age is correlated with unmarried in the negatively, negatively correlated and positively correlated with education. Yeah, we can try. We can try adding both, add education and age. And yes, so this is gonna be formula number 4. And we can add here age, education, and we can add here age. This is gonna be model 4, formula 4, results 4, model 4, and results 4. So we print it. It's here. And you see that coefficient on smoker, if you look at this, does not change that much. Right, so that's probably it signals that these two variables do not lead to the emitted variable bias. So we can include these results to the table. So here we need to put results for regressor order. So let's keep it like this. So the 2 additional regressors are going to be afterwards. And also here in the model names, we need to provide an additional number 4. So in the results table, we put results 4 here. And in model names, we put number 4 here. We run this, we have this nice table. What is interesting that age and education are not significant here. Individually, not significant. Age is not significant, education is not significant. Well, it is reasonable. We cannot say that education somehow affects the birth weight of a baby, right? Education probably can affect whether a person smokes or not, but definitely doesn't affect the birth weight of a baby. And that's what we see here. And age, well, age probably can, right? Because if the mother is older, so probably her health is, she's less healthy, let's say, and probably the birth weight of a baby is going to be less. And look what is also interesting. So adjusted R squared decreases compared to the previous model. So it means that the explanatory power of these two variables is not that strong compared to the previous model. So it is not an evidence that this specification is bad and this specification is good. No, but at least with including these two variables, we see that nothing happens to the effect of smokers. So therefore, at least to some extent, we can believe that this effect is unbiased. Maybe it is still biased. Maybe we can find some other variables that could lead to this emitted variable bias. As I said, an income of a person. If you would know the income, it would be very nice to try including it here, or maybe some metrics of her health and or food consumption. But at least we know that age and education, they do not matter. Okay, is everything clear here with this model?
Yeah.
So let's continue. So we will skip this part E, and now I want to go through several important things related to our lecture. So first of all, I promised you to show, to help mastering something from your home assignment, and you see that in the lectures we also used a statistic called standard error of regression. So let me open one of those lectures. It was lecture 7. And in your home assignment, you also need to compute the standard error of regression. The bad thing that we do not have the standard error of regression reported anywhere in Python, right? So when we are observing this table, unfortunately, there is nothing like standard error of regression. We know how to calculate this. We need to take the sum of squared residuals and divide this by the degrees of freedom. So let's try to do this. Compute standard error of regression for the, let's say, model 2. Let's do some variation in our calculations. So what do we need? We need the sum of squared residuals. And also, for making the joint hypothesis tests, we also need sum of squared residuals for the homoscedasticity only F statistic, right? So that we kill to kind of shoot two goals with this. So sum of squared residuals. How to obtain this? Again, we can use results. Now it is results 2 because we are doing this for the model 2. Results 2. And then there is a simple method called SSR. Sorry, SSR or RSS. Let me check. I'm always confusing with this. Yeah, SSR. Yeah, sum of squared residuals. So this is this number. Very simple. Regarding degrees of freedom, we know.
SSR, or
Yes,
there is
SSR.
also SS res.
No. SSRS refers to this. No, this is not
I
correct.
see.
SSR.
Okay.
Because SSRS, it's some like light blue. It refers you to this object. So now degrees of freedom. We know how to extract degrees of freedom. It's here. And you don't need to do anything. So you just, degrees of freedom is exactly this n minus k minus 1. No need to do anything else. So degrees of freedom is results 2.df resid. And now we are able to calculate the standard error of regression. It equals to square root. So don't forget that this is square root of s squared, and s squared is this fraction. So we take SSRS divided by df and print standard error of regression. So here, this is the standard error of regression. Very simple. If you want to extract r squared,
Again, it is square, not square.
well, we already took a square root. If you divide sum of squared residuals by degrees of freedom only, you have the sample variance of residuals. Once you take a square root, you have the standard error of regression, which is a standard deviation of residuals. And we already took square root here, so that's why we have the standard error of regression. No need to take the square root second time. So how to extract r squared? Well, we can also write something nice like this. Standard error of regression. Model 2 is, and oh, sorry, I forgot to put a comma, so it's here. Well, if you want, you can round this, make it nicer. So now, regarding r squared, same way we use this object results too. You see that as we are already doing, from results, from the object results, we can extract a lot of useful things. So results 2 dot r squared, and you see that there are two r squared, just a simple r squared and adjusted r squared. So if you want r squared as it is, we extract it with this command r squared. Let's compare this with the table 0.07285. Go in here. Yes, we have this 0.0729. So we can call it like r squared equals, and adjusted r squared is results 2 dot r squared adjusted. That's the way how you can extract r squared, and again, you don't need to take them from the table, but if you take from the table, nothing is wrong. This is just not that efficient, let's say. So print r squared is here, r squared, and also print adjusted r squared is then r squared. Well, these two numbers are here. Now let's try to do the following exercise. Let's try to compute this homoscedasticity only F statistic. As we discussed yesterday, this homoscedasticity F statistic is not very efficient because probably the errors are heteroscedastic. But as I said, in many applications, people still use this metric, and well, I can say, well, in this course, we are gonna use heteroscedastic standard error, but if later you will decide to continue your studies on master level and some professor would ask you to compute something like this, at least I must be sure that you know how to deal with this stuff. So let's do the following. So let's test the joint hypothesis that, so let's take what kind of hypothesis we can test. Both smoking and alcohol do not matter for the birth weight. Let's do something like this. So test the joint hypothesis that smoker and smoking and alcohol do not affect birth weight. Or this is gonna be like beta. We would call it, so H null is gonna be that beta 1 equals 0 and beta 2 equals 0. And we are going to do this for model. So let's use model number 2. This one. Or model number 3. No, model number 3. So test the joint hypothesis, smoking alcohol doesn't affect birth weight in model 3. Yeah. So this is our null hypothesis, that beta 1 and beta 2 equals 0. Right? Beta 1, beta 2. We have unrestricted model already. So let me comment it here. So unrestricted model is estimated as model 3. So we have it, no need to estimate the unrestricted model. So now we need to estimate the restricted model. And this restricted model is going to be the following. So let's take everything from estimation of the model number 3. Let's take this part without printing. So we don't want to print all these results. We don't want this table, just this. And let's call this formula rest, like restricted. So how do we do this? This is very simple. We estimate a restricted model, and restricted model, as we discussed, is the model where we believe that the null hypothesis is true, which means that smoker and alcohol do not present in the model. So we drop them. And we keep only number of prenatal visits and whether lady is unmarried or not. So we just drop the first 2 regressors because we hypothesize that these 2 regressors are 0 together. So now model, let's call this model rest, restricted. And here, instead of formula, again, we write formula rest. And here, results, restricted, and model restricted. So nothing is gonna be shown to you after this. We just keep everything inside the results restricted. Now, we need to take this and this. So sum of squared residuals, or let's call this SSR restricted, equals, what is this? We know how to get this sum of squared residuals. We take results restricted dot SSR, right? So results restricted dot SSR. So we are taking sum of squared residuals for the restricted model. So now SSR unrestricted equals results 3, right? Because we are taking this from the third model, dot SSR. Now Q simply equals 2, so no need to extract it from anywhere. We know that there are 2 coefficients here. And here we have what? Here we have the degrees of freedom, degrees of freedom from the unrestricted model, so we can call it like TF unrest equals results 3 TF residual. So we have everything we want for calculation of this F statistic. Very simple. Sum of squared residuals from the restricted model, sum of squared residuals from the unrestricted model, Q equals 2, degrees of freedom are here. So now we can calculate, we can compute F. So F equals, we need to put 2 parentheses here, SSR restricted minus SSR unrestricted divided by Q. So this is the numerator. Now, after the second parenthesis, we can write divided by SSR unrestricted divided by the degrees of freedom unrestricted. Okay, we can print F, and this is the F statistic. Homoscedasticity, only F statistic. So let me know if you have the same number.
Oh, we got 0. Wait a second. Trying to find a mistake.
If you get 0, just try to check the calculation. So probably something is wrong here. Or maybe results restricted. You forgot to drop the regressors. Or maybe you forgot to change somewhere here that results restricted equals model restricted fit. So check all these parts. What about other participants? Vladimir, you have it.
Yes,
No.
I'm following the steps.
What's wrong with your?
I'm checking.
So let's go line by line once again. So first of all, we borrow the third model, the code from the third model, this part of code, and we drop two regressors here. So please be very careful with the names of objects. This is the usual source of any mistakes in the code. Kind of 99% of mistakes happens that you wrote something in the incorrect way. Then the second line, model restricted, and here you need to provide formula restricted, so this object. The third line, results restricted, and you take model restricted from the previous line, and the rest is the same, dot feed, covariance type HC1. So the next part is SSR restricted. We extract from the restricted results some squared residuals. SSR unrestricted, we take this from results 3. So if you ran results 3 before, and if you had this table, then everything should be working. Q equals 2, degrees of freedom from the results 3, and yeah, so be careful also with this F statistic and be careful with the parentheses. So you have one parenthesis for the whole numerator, and the second pair of parentheses here in order to calculate this difference. So maybe this is also the source of a potential mistake here. And in the denominator here, you divide SSR by df.
Yes, I have the chart, and is that the space is necessary? The third and fourth between that? I think no.
So finally, this works.
Yeah, yes.
Perfect.
My answer
Perfect.
differs by 0.3.
So we have 21, 40, 41.
Oh no, I have
47?
22.1. 22.1. Even like that.
If everything is calculated correctly, you must have the same result. So try checking maybe degrees of freedom. You took this from the other model. Okay, so meanwhile, while you're looking for this, or I will upload this code and you can compare your code with this. Let's do the following. So we need to compare this F statistic with the critical value, right? So we put F critical equals. We know how to calculate F critical. It's stats.f.ppf. Now F critical is taken only for 1 minus alpha. Where is that? Yeah, so here. So if alpha is 5%, then for F critical we take 0.95 or 1 minus alpha, so we specified alpha somewhere there, comma, then you need to provide the numerator degrees of freedom, which is Q. So we put Q, and then denominator degrees of freedom, which is df unrest here. And so we print F critical, and it's here. So definitely the conclusion is what? So we see that F statistic is 2144. Critical value is almost 3. What is the conclusion of this joint test?
We reject.
Okay, we reject the joint null hypothesis. And what does this mean?
That
What is the
it,
practical meaning?
that the coefficients are not 0 and they do make sense.
Both coefficients.
Yes.
What is the alternative hypothesis for this joint test? Look, the joint hypothesis is always like this. One or the other or both are not 0, or at least one of them is not 0. So it doesn't mean that both are not 0.
Okay.
So null hypothesis is that both coefficients are 0 together. The alternative hypothesis, as H alternative, is at least one of beta 1 and beta 2 is not 0. At least one. Because later we can, before also we looked at coefficient on alcohol is not statistically significant, right? So if we individually test their significance, alcohol is not statistically significant and smoking is statistically significant. Here we want to test maybe both of them together are not statistically significant, and so that significance is due to random, right? This single coefficient significance. So therefore, at least one of the factors, smoking or alcohol, or both, significantly affect the birth weight. Okay, perfect. So this is the way how we can test a joint hypothesis with the help of homoscedasticity only F statistic. If you are okay with these functions, with extracting sum of squared residuals, you're fine. The same thing you can do with the help of R squared. So you know how to extract R squared from regression results, and you will get exactly the same result for the F statistic. We have 10 minutes to finish, so therefore I'm not going to discuss this with you right now. So now let's do the following. So if you want, you can try do the same with R squared. Instead of SSR, call R squared, and the formula changes slightly, but the result is going to be exactly the same. So now what I want to show you is how to use F test, use heteroscedasticity robust F test. Heteroscedasticity robust F test. So this is going to be the last part which is going to be necessary for your next home assignment. And then in the end, I will show you one thing which is going to be necessary for the home assignment due on Sunday. So how to deal with this? Let's also call results 3 dot, and we can see that there is a method called F-test, which suggests that probably this F-test might help us somehow. Well, the thing is that we can use this F-test in two different ways. The first way is a simple way, but it is not, how to say, very well like in the human readable, let's say, format. So we can do the following. So basically we can call the help here, and we can see that we need to provide this R matrix And this is the example how this R matrix looks like, but yeah, like this. So let me show you what is the logic of this syntax. And basically this syntax is, sometimes it is used, is going to be used in the second part, so we still need to understand this syntax. So you open the parentheses here, and the second parenthesis. So kind of one parenthesis for the function f test. The second parenthesis is needed to provide two sets of restrictions that you put in the joint hypothesis. Then you open the square brackets, and in the square brackets you write the sequence of zeros and ones, and one must be put on the place of a regressor tested. So what does this mean? You put 0. So 0 is for constant, for intercept. Then you put 1, and 1 is for the first regressor being tested. Then 0 and 0. So how many regressors do we have here? 1, 2, 3, 4, 5. Yeah, the fifth 0. So what does this mean? This means that I want to test a null hypothesis that beta 1 is 0, and I kind of specify this with 1. This is one part of my joint hypothesis. Then I put comma, open square brackets once again. Remember that we are doing this in double parentheses here and here. And we do the same 0, 0, 1, 0, 0. So what does this mean? It means that my joint hypothesis, the second part of my joint hypothesis, includes the coefficient beta 2. So once again, you have 5 coefficients, including intercept. You have 5 coefficients. And with zeros and ones, you specify which coefficient you are using in a part of your joint hypothesis. So here you are using the first coefficient, the beta 1, the second coefficient, and here you are using beta 2, the third coefficient. Then you run this part. Oops. Wait a second. Do include constant there? Must be. It is much. Wait a second. 1, 2, 3, 4, 5. What if maybe the coefficient is not, maybe the constant is not needed there? No, must be there. Shape of coefficients. What's wrong with that? Must be working. Let me see. That's the test. What's wrong with that? Okay, so I put it like this. It doesn't work probably. Why it is not working? It was working yesterday. So what am I doing wrong? Okay, so let's try the second approach, and the second approach is going to be the more, let's say, human readable and better. So let's create the object which is called hypothesis. And in this object, in parentheses, you provide the human readable format of hypothesis like this: smoker equals 0, comma, and also in parentheses, alcohol equals 0. So that's it. And let me check. Yeah, the syntax must be like this. Yes, yes. And then you do the same results 3.ftest, and inside the ftest you put hypothesis, this object, and the result is here. So basically this is the better way to provide the hypothesis, joint hypothesis testing. Why? Because in this way you write this explicitly, like what kind of regressor you want to include in the model. Smoker equals 0, alcohol equals 0, and this is already a heteroscedasticity robust F statistic. You see that the number 2178 differs from this number 2144, but basically the difference is not that large, and this means that probably the standard errors are close to being homoscedastic.
Oh,
So
but something wrong. If I write hypothesis with like you wrote, it doesn't work. But if I put I instead of E on the end of the word, it works. Hypothesis.
well, maybe you created the object hypothesis,
Yes.
and yes, so
Yes.
that's the way about.
Sorry.
That's what I'm always telling about the correct syntax. This must also work, and unfortunately I do not know why this is not working. Shape mismatch between coefficients and constants. Yeah, if you do like this, it should not be correct. Yeah, the result is different. But if we put it like this, comma, here, yeah, doesn't work as well. Okay, so I will check this, and we will probably discuss this next time. So this way of making hypothesis F statistic and testing joint hypothesis is okay, right? So you write the hypothesis explicitly and you test this joint hypothesis, and you have, this is heteroscedasticity robust F test. As you see, the F statistic is different to the previous one. Well, this is all I wanted to tell you about the joint hypothesis tests and what is related to our previous material covered in the lecture. And the very last thing, let me do several comments on your pre-last home assignment. So in this home assignment, you are asked to use this data set. This data set is large, and I ask you to do the following. So after you load the data, use these two lines of code. So let me show you, let me demonstrate you how this works. So basically you are asked to extract a specific random sample from from the data provided. So what happens? Let me put this first part of the code here. And once I do this, and once I look at the data, look what happens. It shows me a random sample of observations from the initial data. You see that it took 697th observation, 1536 observation, and so on. So the observations are different. And in total, there are 100 observations. So if I call for the data itself, there are going to be 100 observations. So what happens in this way? In this way, every student doing home assignment will have different sample of the data and different results, which kind of provides you from copying the results from your friends. This is one line here. The problem here is that if I run your code once again, look what happens. If I run this sample once again, and if I open the data, the observations are different. And I cannot check which observations you used for your calculations, right? So this is the problem. So this problem is solved with the first line of the code here, numpy random seed. Instead of I, you will have a specific number. Once you start your home assignment, there is going to be explicitly said that, for example, seed equals 10. And you put instead of I this number, and you work with this. Look what happens if I add this part of code. I run the sample, I extract the random sample, and from this random sample I have these observations, 881, 652, okay. If I rerun my sample once again, wait, what's wrong? Should be working.
Don't you save data as NPC?
No, it should be always the same. What's wrong? What happens? Once I run the seed, it should be the same. Wait, do we have this numpy here? Yes. Well, it should derive me the same sample of the same numbers. So okay, let's probably try something like this. Birth weight. Mean. Yeah, you see that basically the sample is the same, but the elements of the sample are the same, but they are taken in different order. So, for example, if I calculate the mean of a birth weight for this sample, the result is always the same. But if I change seed, for example, to 5, you see that now this is gonna be, this must be different. What happens? What I'm doing wrong? Seed is 1, the same. Data sample. Example. It worked. Probably I'm doing something wrong. Wait. Yeah, you see that now if I don't control for this seed, this changes all the time. Once I put this seed, it is the same all the time. And once I change seed to 2, 3, 4, this number changes. Yes, so probably this part here is somehow wrong. So nevertheless, must be working. It's 5. It's 5. Here on 6, 5, data sample. And so it should work. In your case, it should work. You see that the numbers are the same once you control for this seed. So it is necessary for the system to check your answers and to check that your answers are correct. So that's why, please, when you do this, when you load the data, right after loading the data, use these two pieces of code. This with the seed provided and this with the 100 observations.
Wait, I still don't get it. My average, my mean of birth weight is same for all the seeds.
So once you load the data and yeah, I see what was wrong. Yeah. That's the logic of Python. Look what happens. I will explain you. Look, so now assume that I loaded the data, like the whole data frame without any manipulation here. So you know what happens here. Let's go step by step. So here I specify the seed, for example 6. Here I take my data and I call a new data frame data as well. Then for my sample, look what happens here. For my sample of 5 lines, right, I calculate a birth weight, which is here. Data, birth weight. Now the object data contains 5 observations. And if you want to run this once again, what happens? It takes a sample of 5 elements from this table. So there is a recursion. What must be how we can overcome this problem? So we load the data once again, and the object data must be stored as it is. And here I call this, for example, sample. And once I call this sample, and once I want to calculate for my sample birth weight, yeah, so that's what happens. Mean, look, it will take sample of 5 elements from data, but now this sample of 5 elements is gonna be called sample. So this table is, so the initial table is not changed. You see that initial table data is still consists of 3000 observations, and the new table is called sample, right? And this sample consists of 5 elements. Now when I change seed to, let's say, 120, mean changes because sample changes. Now I have 5 new observations sample from the data, but data doesn't change. So the problem is, once I wanted to demonstrate you that with the change of seed, mean changes, I needed to change the name of my of this sample data to another name, like give it a new name, because in this case the initial data set is not affected and the initial data set is still here, and I sample from it again and again. Because look, again, if I change seed, mean changes, sample changes, initial data doesn't change. Because if I do this, what happens? I rewrite my initial data with a new table, and this new table consists of 5 elements only. Look, if I do like this, so my data, my initial table is changed. I rewrote it. But in your case, in the case of a home assignment, you don't need to sample this again and again and again. So therefore, if you put it like this, here if you put it like this, everything is going to be okay, because you don't need to resample this again and again. You need to sample this once and then work with what you have in this data consisting of 100 observations. You simply don't need all the other observations. So this is a pitfall of giving incorrect names in Python.
And why do we need this?
To have different data for different students.
Okay.
So the data set is large, and each student will have different numbers, such that you don't copy your answers from each other. Okay, that's it that I wanted to tell you. Anything that we still need to discuss? So before making home assignment, try this sample. Try that you know that everything works and you understand how this works. Because if you try to do this during the home assignment, so probably you will panic and you will do some mistakes. There is a tutorial on this. So the link is here. Yes, the very last thing that I wanted to tell you. So the tutorial is here. So I explained how this sampling works there. Quiz number 5 is available till tomorrow. Home assignment number 4 is going to be available shortly. So I hope during this day until the next Sunday, Sunday 22nd, right? Yeah, Sunday 22nd. What else? Yes, I put here the recordings of previous 2 exercise sessions, exercise session 6 and 7, in order if you need to refer. And this exercise session is also recorded, and I also put it here, and the link is going to be available here, so you can rewatch all the steps and hope it will help you mastering the home assignment. I guess now that's absolutely all that I wanted to tell you.
Wait, we have home assignment 3 and 4, right?